All right, let's start the next session. It's a pleasure to have Ashoke back in front and to tell us more details about his calculations.
Thank you. Thank you. Okay. So yesterday I gave a somewhat general overview of the results. So today I am going to explain some of the calculations and focusing entirely on the classical approach. We will not discuss quantum soft theorem today. Okay, maybe at the end, if I have some time, I may say a few words. But the main focus of today's lecture will be on the classical analysis, and we will see how the results that I quoted, at least some of the results that I quoted, can be obtained from direct classical analysis. Okay. So some part of this I discussed yesterday, but as probably went through somewhat of a hurry. So let me repeat again. Okay, what is the procedure that we are going to follow? Okay. So the goal is to find the gravitational waveform, or equivalently the trace reversed version of the gravitational waveform, which is called E mu nu, okay, that is generated during the collision process. So the starting point will be the field equations, okay, and we will be using the redundant gauge or the harmonic gauge, and in this gauge the Einstein's equation that determine E mu nu takes the following form. Now this looks too simple, right, because this is something that will solve for electrodynamics, for example, which is a linear theory, okay, but it's deceptive because all the nonlinearities of Einstein's equation have gone to the right hand side. Okay, so all that we have done is that we have taken the Einstein's equation, the left hand side of the Einstein's equation, identified the linear part, right, which is this box of E mu nu, and everything else I have put on the right hand side and absorbed into the definition of T mu nu. So this includes the usual energy momentum tensor, but also the nonlinear part of the Einstein's equation. And because of this, it clearly also has explicit dependence on the fields themselves, right, in particular the E or equivalently H. And because it also involves the usual energy momentum tensor, it will involve trajectories of various objects that are involved in the scattering. And these trajectories, of course, are also controlled by the gravitational field itself. So it's a set of coupled differential equations that we have to solve. So in this analysis, we are going to introduce two kinds of Fourier transforms. Okay, so given a function of space-time coordinates t and x, I'll use the symbol tilde, okay, to denote Fourier transform with respect to the time variable only, right, integral dt to the I omega t, and this factor has been introduced just to make sure ensure that this t, the Fourier transform here is really with respect to retarded time, because to leading order t minus mod x is a retarded time, right, because this is the time at which the peak of the signal will reach the detector. And the second kind of Fourier transform will be the full Fourier transform, which I'll denote by hat, okay, and that's given here. And we will see that both of these will be used during the analysis. Here are some mathematical results, okay, which you can also verify easily. That the memory term, for example, is a constant jump. So E mu nu vanishes at early time and it goes to a constant at late time. This kind of behavior of the position space wave function, so that means if E mu nu of t and x have this kind of behavior, then the corresponding Fourier transform, the time Fourier transform, has the feature that it goes as omega inverse for small omega. And a general feature is that the late and early time behavior in position space, okay, correspond to controls the behavior of the Fourier transform for small frequency, right. This is a general feature, and we see here that late time behavior of E mu nu is controlling the omega goes to 0 limit of the Fourier transform. Similarly, one can verify that if E mu nu goes as 1 over u for large u, then this will correspond to a term proportional to log omega in E tilde mu nu. Later on, will distinguish between whether it goes as 1 over u for large positive u or 1 over u for large negative u. But the general feature is that whether it's positive u or negative u, this kind of behavior translates to a logarithmic behavior of E tilde mu nu for small omega. And similarly, a log u over u square kind of behavior of E mu nu at large u will correspond to a omega log omega square behavior of E tilde mu nu. And one feature that is common to all of these is that these are non-analytic. And as I described yesterday, what we mean by non-analytic function is not that the function itself should diverge. These do, but this doesn't. But that if we take sufficient number of derivatives with respect to omega, then eventually the function will diverge. Right? For example, this one, if you take the first derivative with respect to omega, you get a divergent term proportional to log omega square. If there are any questions, please feel free to ask at any stage. So this is the equation that we want to solve, and here is a formal solution that we can write E mu nu simply as the integral of the retarded Green's function multiplied by the source. Now we will be analyzing this E tilde mu nu omega. This should be vector x. I think this is there's some take error here. So you are looking at the time Fourier transform of this function of E mu nu. Okay, so that this is the definition of the time Fourier transform. And now to analyze this, we substitute for E mu nu this expression over here. Okay, so that's done in the second line here. And the only extra ingredient in the second line is that this retarded Green's function I have expressed in terms of Fourier transform. You are familiar with Feynman propagators, right? L square, the 1 over L square is the Feynman propagator. Retarded propagator is very similar except that the I epsilon prescription is different. Right? For a Feynman propagator, the I epsilon will be outside. Here, I epsilon comes with L0 plus I epsilon. Okay, so this, all that we have done in going from first to the second step is to use this expression over here. In the next step, we have performed the t integral because you see the t dependence is through this e to the I omega t and e to the minus I L0 t. So the t integral will give a delta function that sets omega equal to L0. Okay. So t integral is done and then the L0 integral can also be done because L0 has to be just set equal to omega because of this delta function. So that's this step over here. So we have this integral as it is, and instead of getting a 4-dimensional integral, we have a 3-dimensional integral. Okay. And everywhere there is L0, we have replaced by omega. Now at this stage, we use the fact that our eventual interest will be to calculate this E mu nu. Okay, when you want to calculate the waveform of the detector, we want to calculate this E mu nu at large mod x. So in other words, you want to evaluate this at large mod x. First of all, okay, if we can do that, so you can decompose L vector into its component parallel to x and transverse to x. Right? It's a 3-dimensional vector, so you can always decompose into the parallel component and the transverse component. So L square you can write as L parallel square plus L perpendicular vector square. L parallel integral you can do by Cauchy's theorem because you can just close the contour of integration of L parallel and complete the contour and use Cauchy's residue theorem. Okay. So that's the way you can do the L parallel integral. Okay. After picking up the residue, one can show that for large x, you can evaluate the perpendicular L perpendicular integral, which is a 2-dimensional integral. Okay. by a saddle point method, right? Because for large mod x, the saddle point approximation becomes good. The exponent is sharply peaked around some particular value. So you can do the L-Parp integral using saddle point. And the net result of this analysis is that you have the simple expression for E tilde mu nu, where the L integral is completely done and you have an expression of this form. This vector k, this is a 4 vector, but it's controlled by omega, right? Because of course on this side there is no, you have only taken the time Fourier transform, right? So this k is given by omega times 1, the first component is 1 and the second spatial component is the direction cosine of the source of the detector. So this will be a formula that will be used critically in our analysis. Are there questions on this? Okay, so here is the same formula again. And yes, yesterday we discussed how to analyze this. Namely that once you have an integral like this, we can divide the integral over y into 2 parts. One we will call the scattering region, which is where all the interesting things happen, right? Where the particles interact. There may be nuclear explosion here. Okay, they can exchange mass, they can exchange energy. And then the complement, which is the asymptotic region, right? Here, the only forces that operate are the long-range electromagnetic and gravitational forces. Right? That's what distinguishes this region S from the rest. And now the idea is that if we are looking for non-analytic terms in E tilde, right? Recall non-analytic terms means that if we take sufficiently large number of derivatives with respect to omega and then set omega equal to 0, it should diverge. Now as you take derivative with respect to omega, omega appears here, right? K is here. So as you take derivative with respect to omega, you bring down powers of y. But as long as the y integral is over a finite region, that can never diverge. Okay, because you will get maybe very large power of y, but nevertheless it's a finite volume and hence it will always give a finite answer. Okay, assuming of course that the configuration is non-singular, so T mu nu should be well defined everywhere. So that shows that in order to focus on the singular part, okay, which is what we need because this is what we are looking for, right? The singular part, the non-analytic part, we can focus on the asymptotic region. And in the asymptotic region, first of all, the forces that operate are the long-range forces, and because it's far away from the place where the scattering is taking place, we expect that the fields will be weak. Right? So E mu nu will be small in the asymptotic region, and hence we can try to iteratively solve this. So this is what I have explained in the next slide, that in this integral we can restrict the y integral to the region outside S. So in this region only long range forces are important. And furthermore, because we are far away from the place where scattering is taking place, we expect that E mu nu should be small, and so T mu nu will simplify and the equations can be solved iteratively. Okay. Doesn't mean that you can only stop at the first order, right? You have to keep systematically correcting it. Okay. Nevertheless, there is a iterative procedure that you can use because of the fact that the fields are weak in this region. Is this clear? Are there questions? Okay, so in this slide, I have given a summary of all the equations that we need for carrying out this iteration. So the first line, this expression is the expression for the energy momentum tensor due to the matter fields, right? Due to the particles which are coming out of this scattering region. Okay, so these are the energy momentum tensor of the particle trajectories associated with these particle trajectories. The top line is the outgoing particles, and the bottom line are the incoming particles. The second line tells us that the total energy momentum tensor, the way we have introduced this T mu nu, is the sum of the matter contribution, but there is also a contribution from the gravitational field. Right? And in fact, this contribution has quadratic term, cubic term to arbitrary non-polynomial term, right? Because Einstein's equation doesn't stop, right? Because you have to take the inverse of the metric or the determinant of the metric, right? So, and that goes on forever. Now, I said that I have summarized all the equations, but I have not given the expression for TH. This will appear when you need it, right? But other than that, this contains all the equations that we'll be using. So this equation we have already seen earlier. This is the Einstein's equation written in this form. And these are the trajectory equations, right? These tell us how the x's evolve in time for a given metric, for given E mu nu or equivalently G mu nu. These are for the incoming, these are for the outgoing particles, these are for the incoming particles. And now the key point, okay, and that is how we put the boundary condition. So normally in a classical problem, right, in a classical problem which is time dependent problem, right, the way we set up the problem is we specify the initial value of all the fields, all the particles, and then evolve with time using the equations of motion. Here we are not doing that. What we are doing here is that for we set the initial values, we put initial condition for the incoming particles, okay, but final condition for the outgoing particles. You see here, so we are specifying both the incoming momentum and the outgoing momentum. For the gravitational field, we will use the usual boundary condition that in the far past the gravitational field was 0. Okay, and then we want to compute what happens as we time evolve it. Okay. So this is a crucial difference between the usual classical approach to solving problems of this kind and what we are doing in this case. Okay. And the reason that we are doing it this way is because our fundamental goal is that we say that we know what particles went in, what particles went out. Okay. Given that, we want to compute the radiation. Okay. We want to compute the late time tail of the radiation. So we in a sense already assume that we know the final state of the matter particles. I'll come back to this later. Okay, that this is in fact what soft theorem teaches us, what quantum gravity teaches us as opposed to classical gravity. Because it's only in a quantum field theory, okay, that the way we set up a problem, right, you set up a problem in terms of calculating S matrix, where you specify both the initial and the final state, and you calculate probability. Okay. In a normal classical approach, you will not do this. Okay. But if you don't do this, then of course the problem becomes much more complicated, okay, because there you will try to evolve the equations of motion in forward. Okay, and you have to calculate simultaneously what kind of radiation is emitted and also what kind of particle trajectories you get at the final time. Okay, and that would have been much more complicated problem than what we are trying to solve here. Are there questions on this? Yes. Well, classical scattering, but you are not specifying what kind of forces are acting on it in the middle. Okay. So what we are saying is that imagine that some forces act on it and you produce some final state. Okay. And we want to know, given that it's a conditional approach, right? That given this, we know the initial particles, we know the final particles, right? There will be some interaction which will produce those final states, right? But that's perhaps not so too important. But given that data, how to calculate the radiation from this process? Okay? If this process is not possible for some reason, right, then this answer is irrelevant, right? Because you will never get final states of this kind. Yes, true. So at this stage, I am assuming that the particles are uncharged, so there is no electromagnetic force. Right? But if, for example, there are charged particles, these equations will get corrected. Right? I am not showing this, but they can certainly be taken into account. Right? And if it happens that there are other long-range forces, you have to include their effect as well.
The radiation will also include photons?
Yeah, the radiation will also include photons, right? But those have to be calculated separately, right? Because this will calculate gravitational radiation, right? For the photons, you have to write a corresponding Maxwell's equation, right? And that will calculate the photon radiation. Yes.
Technical question. So, could you go back a couple of slides?
Go back. One more?
One more.
This one?
Yeah, so here you're doing a large X expansion.
Yes.
So in some sense, even when you do the Y integral later, where you are integrating outside of the region outside of the source, you're still considering the detector to be out of.
Yeah, so detector is far away, right? Far away. But I should say that I'm not going to use this expression, right, for calculating the E's which are here, which appear inside this. Right? For these, I have to use the exact E's, right? Because these are not at infinity, they are not far away, right? So the E's that will enter here are not the E that I wrote, right? That E is the final E that we have to calculate at the detector, indeed. Okay, so the other point I wanted to mention is that yesterday there was a question that if you have this example of a bullet cluster, right, whether you should use the bullet cluster as one object or made of many objects, right? What goes in, what are the PIs that will go in? Basically, it doesn't matter, and the point is that this is the way the momenta are going to enter the analysis, right? So what matters is the total energy momentum tensor that these sources carry. And the energy momentum tensor of the bullet cluster you can calculate either by thinking of the bullet cluster as one object or as sum of multiple objects. Right? They will eventually give the same result. So in the final expression, that's a consistency check. You can check that indeed it satisfies that condition, that if we take a particular outgoing momentum Pa, okay, and replace it by two outgoing momentum, one is x times Pa, the other one is 1 minus x times Pa, the answer will be the same. Right? And the formula that we have actually does satisfy that condition. Right? That's a consistency condition. But the reason that condition is satisfied is because of this, that the way the trajectories are entering the actual analysis is through the energy momentum tensor that the trajectories are carrying. Any other question here? Okay. So the strategy that we will be following, this is not necessary, right? But this is what we had found convenient, is to write out all the equations in momentum space and then solve them. Okay. Momentum space means the Fourier space. Okay, we are going to work with the hatted objects, right? Write the equations in terms of the hatted quantities, okay? And then eventually, of course, you have to go back to the position space. So let's start the iteration. Okay, so at the leading order, we can set E mu nu equal to 0. Okay, no gravitational field. Okay, and the only source of energy momentum tensor is a matter, so Tx mu nu. Okay, and Tx mu nu is given here. Now it turns out that one can use a slightly convenient notation instead of writing both the outgoing and incoming particles separately. Okay, we'll treat the incoming particles as outgoing particles with momentum minus p prime and proper time minus tau, and write one single expression for Tx. Okay, so that basically this allows us to write things in one line instead of two lines. Okay. So sigma here is tau for outgoing particles and minus tau for incoming particles, right? But this contains exactly the same information as this one. So we are going to use this expression for Tx, okay, and do the first iteration. We are going to solve this. So to calculate this Tx, we have to know the trajectory, and in the leading order, the trajectory is that of a free particle. Okay, so this is the proper velocity, sigma is the proper time, so x mu is proper velocity times proper time, and then there is a constant part, that is constant term that you can add. Okay, but this will not, this will basically drop out in the final expression. Okay, so this RA, this constants basically tell us this is in some sense the size of the scattering region, right? If you look here, this picture, right? What is RA telling us? RA telling us that if we extrapolate these trajectories back to the origin where the scattering took place, right? All these trajectories extrapolated may not meet at the same point, right? Because during the scattering they may have gotten displaced, but those RAs are basically controlling the parameters the size of the scattering region. Okay? That's all you need to know. We don't really need any detailed information about those RAs. Okay, so T mu nu to this order is just Tx. Okay, and as I said, we will be working with the Fourier transform variable. So let's calculate T hat. So T hat is the Fourier transform. Okay, nothing new has happened. All I have done is that I have used this convention over here. Then using this delta function, this is the 4-dimensional delta function, I can do the x integral, right? And write this, just replace this small x over here by the trajectory xa of sigma. Next step, I substitute for xa of sigma this trajectory equation which is here, okay, and dx d sigma is just p over m, right? So here m was in the numerator, but because you have two factors of m in the denominator, this has become m inverse. Now you have to do the sigma integral, right? It's exponential, so it's easy to do, right? But here there is a small point which is important, and that is, you see, the sigma integral is oscillatory, right? At the upper end it oscillates. But what we can do is that we can introduce an I epsilon so that this integral is damped. And the way one can introduce the I epsilon is to replace k dot pa that appears here by k dot pa minus I epsilon, because you see there is a minus I that is multiplying the whole expression, right? So if k dot pa has a minus I epsilon, right, then it's minus I times minus I epsilon, that's minus epsilon. So the integral is damped at sigma goes to infinity. Okay. So that's what tells us what kind of epsilon that we should use here, right? That the epsilon is positive and this is the correct I epsilon prescription. Is this clear? Are there questions?
Because this T mu nu,
Yes.
that with was just P mu P nu.
Yes.
And what is the significance of this T mu nu K? In the sense that this extra soft factor, this is that first term in the soft factor. But what is the meaning here?
This one. No, I'm just calculating the Fourier transform of T hat, right?
Yeah, but normally it is just P mu P nu.
No. Because this is the full Fourier transform.
Yeah, that's
Right?
an extra factor that.
See, I used, if I had used the, okay, in the position space, it would be p mu p nu, right? This is just p mu p nu, right? And then this is telling us that it's localized on the trajectory, right? Now you are taking the full Fourier transform of this object, right? Full Fourier transform means because of this delta function, I replace x, small x by capital X, e to the I k dot x, and now we do the sigma integral. Yeah, so this is really t hat. I mean, here at least I have not done any approximation, right? Starting from here to here, it's an exact analysis. Okay. The only subtle point here is I epsilon, right? And that is needed, that is chosen in such a way that this integral converges, right? We have to really think of this as analytic continuation from the lower half k dot p plane, right? Because that's where this integral is convergent. That's all it means. Is this clear? Okay. And why are we calculating t hat? Okay. That's because ultimately at the detector, let me show you that formula. Okay. This is t hat. Okay. So when you want to calculate a gravitational waveform, right, the Fourier transform, we have to calculate t hat. Right? That's the reason why you are calculating this t hat. Okay, so at this stage you are going to make an approximation because you are ultimately interested in omega goes to 0 or k goes to 0 limit. So these terms can be ignored at this stage. Okay, so it's just given by this. Yes.
So then the P mu is just the free particle, and this is the free particle which has emitted a graviton of k.
Yeah, because E mu nu, right? The t hat mu nu is E mu nu that we saw, right? That's because at the far away detector, right? That analysis that I did using the saddle point, right? That the far away detector is a full Fourier transform of T mu nu, that is the waveform.
So this has an extra particle there.
See, this is T hat mu nu. I mean, this is a Fourier transform, right? At this stage, it has no extra particle. You can, this is related to the gravitational waveform because of this equation. Because we did this analysis here to show this, right? But this by itself is just a well-defined object. This is a Fourier transform of T mu nu, right? And what I have given is what you have. Right? So if somebody gave you the T mu nu of a free particle, right, and asked you to calculate its full Fourier transform, right, without saying why you need it, right, you will still get to this expression. Right? There's nothing, I mean, you can't change it. Right? So this 1 over k dot p minus I epsilon, it looks like a soft factor, right? But at this stage, it's just part of the Fourier transform. Right? This is what you get. Fourier transform of T mu nu has this factor. Right? You have not really done anything in this page. Right? There is no soft. There is no. I mean, we're not doing any soft analysis, right? Except that at this stage we just drop this because k is soft. Any other question? P mu prime? Yeah, because of this, yeah, so this includes both incoming and outgoing particles, right? So P should be thought of as minus P prime for the ingoing objects. Okay, so this is the same equation repeated. Now, let's look at this I epsilon term a little more detail. So k dot Pa is minus omega times P0A because the zeroth component is omega, right? And then there is also omega n hat dot Pa, okay? And then this minus I epsilon. Okay? So E tilde mu nu, right? Now we are going to use this result, right? That the reason that we calculated T hat mu nu is because E tilde mu nu omega x is ultimately going to be related to this. This is the gravitational waveform at the detector, right? Which is related to the Fourier transform of the energy momentum tensor. Okay? So E tilde mu nu is then given by this. And from this, we can now calculate E mu nu, okay, by Fourier transform, inverse Fourier transform, right? So E mu nu is given in terms of E tilde mu nu by this expression over here. This is the only extra phase, and that is the way, because of the way we had defined E tilde mu nu. Let me go back and show this. The definition of E tilde mu nu. Yeah. See, E tilde mu nu definition had this e to the minus I omega x factor, so that's why you get this e to the I omega x. Okay, so we have to now, to calculate the gravitational wave form in position space, we have to evaluate this integral. Right? U, I have now used the fact that u is t minus r. Okay, so that's why I have replaced this by e to the minus omega u, that's the retarded time. So how do we evaluate this integral? Right, we will again use the Cauchy's theorem. So for outgoing particles, okay, so this is not Cauchy's theorem, this is just a observation, okay, that for outgoing particles, energy is positive. Right? And so if you look at this expression over here, then in the omega plane, we can see that the pole is in the lower half plane, right? Because PA0 is positive, so the pole is in the lower half plane. And for incoming particles, the energy is negative because PA0 is really minus P prime A0, and so the pole is in the upper half plane. Now we come to Cauchy's theorem. That suppose u is positive, right? That's late time. If u is positive, we have to close the contour in the lower half plane, right? Because you want to make sure that the contribution from the asymptotic part is convergent, it's damped, right? So you have to close the omega contour in the lower half plane for positive u. Okay? And then because of this observation, we see that we pick up contribution from outgoing particles, right? This integral can be evaluated using residue theorem, but in terms of outgoing particles. And for negative u, we have to close the contour in the upper half plane, and we will pick contribution from the incoming particles. Okay, so this is now a straightforward analysis using Cauchy's theorem. So this is again the repetition of whatever equation I had written. But after applying Cauchy's theorem, we get this expression for E mu nu. For large positive u, we have this expression over here, and for large negative u, we have this expression over here. Is this clear? Right? We just evaluated that those integrals by closing the omega integration contour in the upper or lower half plane. Now you see that this kind of expression is of course the correct evaluation of the integrals, but this is not what we had started with, because we had said that we will choose our initial condition so that the gravitational field is 0 at far past. Right? Here it looks like it's not quite 0 in the far past. Okay. But this can easily be made 0 by coordinate transformation, okay, because this is a constant. Okay. So you can always add a constant to gravitational field to g mu nu to make this into 0, but the price you pay is that the same constant now has to be added to late time. Okay. So what matters is really the difference between these, right? Not what it becomes at far past or far future by itself. Okay. So we make E mu nu vanish for large negative u by adding a constant to it, and then get the E at late time to be given by this. Okay. And if you recall the expression for A mu nu that I had written down, it's precisely this. Okay, so that's the calculation of A mu nu or the memory effect.
Which point did you put in the fact that this is asymptotic outside the S region?
Oh, because we are using this iteration, right? This is the first iteration. Because otherwise, E mu nu, I mean, you cannot use iteration, right? You have to include the TH effects, right? The fact that we are using only the matter energy momentum tensor and not TH, right, is because your TH is small, right? And TH will be small only in the asymptotic region, right? In general, otherwise TH will not be small.
You got this result by setting the p prime to minus p. So it's like that factor that you get is actually just 0, right? In the leading order.
No. P not P prime is minus P. Okay, let me. P prime is not minus P. See, the point is here there is sum from 1 to n and then there is sum from 1 to m, right? All we are saying is that this sum will extend to m plus n, right? And n plus 1th p will define as minus p prime 1. N plus 2th p will define as minus p prime 2 and so on. Right? So it's not that the original p's are set equal to minus p prime. Right? That we had p1 to pn, and now you are saying let's introduce pn plus 1 to pn plus m, right? Which are minus p1 prime to minus pm prime. Right? So these are independent objects, right? From 1 to n is outgoing, and from n plus 1 to m plus n is the incoming. Is that okay? Are there other questions? Okay, so if this is clear, then you are going to proceed to the next step, next iteration. Right? So the A mean you have got, now let's check how to calculate B and C. Right? And then I am not going to proceed beyond that, F and G, right? But I will just say how it is done.
So this iteration works only if the graviton is less compared to the PA.
Not the energy of the finite energy gravitons. Those are included in PA. Right? Because you are saying, so when you talk about the outgoing particles, right? This includes both the matter as well as the finite energy gravitons. Those you are just treating as matter. Right? So the sum over A includes also the outgoing gravitons, outgoing finite energy gravitons.
So where is the soft graviton part in this?
The TH. The TH will be the soft graviton energy, right? Which I will calculate. This E is the soft graviton to first order, right? The source of E we have taken to be the TX, and the TX includes both the usual ordinary matter particle as well as the finite energy gravitons. Okay, that whole flux is included in this TX. Is this clear? Right? That's the way we are doing this approximation, right? So when you say the gravitational field is small, right, is the soft gravitational field that is small, right? The late time behavior that is small, and that's what we are using here, the smallness of E. Any other question? Okay, so now we have to go to the next order. So let's review what we have at the end of the first order. So the expression that I gave here, this was as a detector, right? But when you want to go to the next order iteration, you don't want to calculate E at the detector, you want to calculate E also at the finite region, just in the asymptotic region, right? Because you have to see how it affects the trajectories of the other particles. Okay? So now we have to calculate E without making this detector approximation, large R approximation. So you have to use the complete expression. So where did this come from? Okay, this came basically this is a momentum space representation of this this one. Okay, this is an exact expression, of course, and on this other side T was replaced by Tx. So in position space you have an integral, but in the momentum space it's just a multiplication, right? GR you have to use the retarded propagator in momentum space, and for this you have to use the Fourier transform in the momentum space, which is T hat. So this is the expression for E hat at the next iteration without making large R approximation. And T hat mu nu, of course, you have already calculated, which is here. And again, I should emphasize here that T hat calculation, we have not made any larger approximation. T hat is just a Fourier transform. The larger approximation has gone in when we relate the E at the detector to T hat. But as far as T hat is concerned, this is what we have at the end of our iteration. Right? No larger approximation has been made. So that's what we are using here. Okay. So this is the fact, this just reflects the fact that E is a retarded Green's function convoluted with T, okay, the momentum space version of this, and now we are using the expression for T hat that we had just found. Gr of k is given here, this is the retarded Green's function. So from this we can get E mu nu and H mu nu, okay, by the Fourier transform of these objects, right? Because once you know E hat, right, E is just a Fourier transform of this, right? Because that's the definition of E, that's what relates E and E hat, full Fourier transform, right? That's what we have written here. So these expressions give the value of the soft graviton, the value of the soft graviton field, okay, at finite point x, right? Because that's what we are going to use now to calculate the Christoffel symbol and see how it affects the motion of the other particles. So this is the equation, right? And so we have to calculate how much contribution you get for the Christoffel symbol. That's straightforward, right? Because we know the expression for the Christoffel symbol in terms of the gravitational field. So we substitute. Okay. And using this, we can calculate how much the trajectory deviates from what we had originally taken it to be. Originally, if you recall, it was a straight line trajectory, PA over MA sigma plus RA. Now, this gives you how much it deviates because of the right hand side that appears here. So the idea is that we will express this gamma in terms of E, right? And E is given by this to first order and calculate how much is the change in the trajectory, because that in turn will determine how much is the change in Tx, right? Because Tx depend on the trajectory x. Okay, so here is delta x, E mu nu, you know what it is. So using this E mu nu calculate gamma, and using that to calculate delta x. And using that in turn, we calculate how much is the correction to T mu nu. Okay, just because of this should have been actually Tx mu nu, right? This is not the full T because there is also the gravitational energy momentum tensor contribution. So both of these equations should also have a capital X in it. So let me repeat again, right? So this expression gives you how much T hat changes, and we have already found an expression for this, right? Because we have this. And gamma we can calculate because we know expression for gamma in terms of E or H, and E and H have been determined at the level of the first iteration. So the idea is that we calculate everything in the we write everything in the momentum space, okay? And once you write in the momentum space, one can show that the integration over these sigma prime and sigma double prime and sigma prime variables become easy, right? They basically become integrals of this kind, what we performed here. Yeah, they basically become integrals of this kind and give you factors of this kind, okay, after you do the sigma integral. So I'll now write down the result that one gets. So by doing this analysis, we get an expression for delta T hat x. This is Fourier transform, and we see all these 1 over L dot PV minus I epsilon, 1 over L dot PA plus I epsilon. These are all coming from the sigma prime integrals. Now you notice that this looks like Feynman integrals, right? I mean, if you want to evaluate a Feynman graph, okay, these are the kind of integrals one finds, right? Except that these propagators are not quite the same, okay, but they are roughly of the same kind. And what are you trying to look for? We want to evaluate this in the small k limit, because this delta T hat x will contribute to delta E tilde, because E tilde is directly related to T hat, right? Because there's 2G over mod x times E hat. So once we can calculate how much D hat X changes, okay, we can calculate how much E changes. So now the idea is that we want to evaluate this in the small k limit, okay, and what we are looking for is a singular term, right? If you recall, the next order we are expecting some log omega term, right? And so what we are looking for is a log omega contribution from this integral. Okay. And even though the integral looks somewhat complicated, okay, these kinds of expressions are exactly what people analyze in gauge theories, for example. In perturbative gauge theories, right, when you evaluate Feynman diagrams and when you try to calculate the leading log contribution to Feynman diagrams, it's exactly these kinds of integrals that one has to analyze. Okay. So you basically use the same technique, right? The kind of technique that one uses in quantum field theory, perturbative quantum field theory, to calculate leading logs, okay, is what we use to evaluate these integrals and extract the log omega piece from here.
This is a language. This would be called a loop integral because you are integrating.
Indeed, yeah.
So, but you derive this classically.
Yeah, this is purely classical.
So normally one thinks that classically the Feynman diagram is just a T level. There is no.
Yeah, so I think that is a misnomer because that is from the point of view of quantum field theory, from fields, right? Classical field, if you are doing classical field theory, then that's three-level classical, three-level Feynman diagram. But what we have here is not just classical field, right? We have the external particles which are heavy, right? And so even at the classical level, you get loop integral looking things, right? But of course, you have not done any quantum mechanics anywhere, right? There's no H bar. I mean, the whole expression came just from classical analysis. It just so happens that the integrals that you get are the kind that appears in Feynman diagrams.
It's not a genuine loop integral.
Yeah, it's not a genuine loop integral because we are not doing quantum field theory, right? There's no H bar in this anywhere.
The same thing if you wanted to express in terms of Feynman diagram.
Yeah.
How would you?
Yeah, so there people use this KMOC formalism, right? But in that you cannot really do the kind of analysis we are doing here because here we are not assuming anything about how hard the scattering is, right? This kind of very hard scattering. Because as I said, the incoming momenta and outgoing momenta can be completely different, right? In KMOC, what people do is to do some large impact parameter scattering where you start the quantum amplitude and try to take the classical limit. But that I think will be limited. Wherever they overlap, they would agree, right? I think the Chennai group, for example, did reproduce part of the soft results, right? In specific examples where the impact parameter is large, right? So low angle scattering, right? They verified that KMSC gives the same result as what soft theorem gives. But here you are not assuming anything about impact parameter. They can be really hard scattering. Okay? We are just applying this, the purely classical equations of motion in the asymptotic region, right? And the fact that we are getting Feynman diagram like integrals is just, it happens to be that way. Okay, so as I said, right, this is something that people study in perturbative quantum field theory, right? And we basically use the same technique to extract the log omega piece, right? And here it is. You see the some constant L that has appeared here. L basically is an intrinsic ultraviolet cutoff, right? That is actually inbuilt in this integral, right? Now, in Feynman diagram, you all have some natural UV cutoff. Okay, you use dimensional regularization or you use something else. So there is an UV cutoff that we introduce. Here, of course, you are doing classical theory, right? So there is no UV divergence. So the UV divergence is automatically controlled by these exponential factors over here, right? These are the ones that are not normally present in Feynman diagrams. Okay? So what this is saying is that when K and when this L loop integral becomes large compared to this combination, then this becomes an oscillatory factor, right? And those oscillations basically kill the logarithmic divergence that these integrals have. Okay? So effectively there is a natural cutoff which is 1 over RB minus RA, and that's the size of the scattering region. Okay, so and that's what we get So this evaluation I will not do, but this is, as I said, we use the standard kind of technique that people use in perturbative quantum field theory to evaluate this integral. Some notation, here you have this eta A, eta B. So eta A by definition is 1 for outgoing B and -1 for incoming B. Right? Because you see here again you are treating the incoming and outgoing particles together, right? But you can separate it out. And this eta A, eta B equal to 1 basically means that the pair AB have to be both outgoing or both incoming. Right? That's the only combination that contributes to this sum. Are there questions?
Impact parameter kind of thing appears like a UV cutoff in this L.
Yeah, if you think of that as the impact parameter, scattering region size, yeah, indeed. Right, but you don't need to assume that it's large or anything. It has any order unity cutoff will be fine. Because our real interest is in this omega dependence. Okay, but you are not done yet, because what you have done so far is to calculate how much Tx changes by the first order correction. Right? But the total energy momentum tensor at this level also has a contribution from the gravitational energy momentum tensor, Th. Okay. So Th is complicated, right? Because Einstein's equation is indeed complicated. So this is the quadratic part of Th, and then the order h cube corrections. Okay. But it turns out that at this order we only need to look at the quadratic part of h. So the idea is that we have already calculated h at the first order, right? Let me show you that expression again. Here, E mu nu we know, right? From the leading order calculation, and from E you can calculate h. So you just substitute this expression into that integral, okay? And then take the Fourier transform to calculate t hat. So basically then we use the fact that the products become convolutions in momentum space, right? And we just, it's a straightforward analysis. Okay. So let me show you what result one gets, right? T hat h, right? After you take the Fourier transform, okay, we get an expression of this kind, right? You can recognize that this is, the two h's are appearing, one here, grk minus L times 1 over pa dot k minus L minus I epsilon. The other h is grl times 1 over pb dot L minus I epsilon, and this combination, okay, is what we see here, okay, is basically this Fourier transform of this combination over here. But the upshot is that this is again a Feynman diagram like integral, right? Because we have propagators, okay, with grk minus L is just 1 over k minus L square with some appropriate I epsilon. Similarly, grl is 1 over L square with some appropriate I epsilon, right? And these are some numerical numerator factors that we often have in Feynman diagrams. So we now apply again the same Feynman diagram method to evaluate this integral, okay? In particular to extract the piece that is proportional to log omega, right? Because that's what we are trying to, the singular part is what we are trying to extract at this stage. Any question? And this is what one gets, T hat h. Okay, again a complicated expression, but you do it by using the same perturbative field, quantum field theory techniques. So at this order, that's all you have, right? So let's add them and see what we get. So after you add them, so this is, okay,
Sorry,
so you add them, I have not added them here.
Could you go to the previous slide?
Yeah.
So here you get the capital R in the log.
Yeah, you get capital R. Maybe I should explain where that comes from. Right? So unlike the previous integral, right, which had UV divergence, right, and that is controlled by this exponential factor, right? Here this integral has both UV and IR divergence, right? This is divergence both in the UV and the IR. Right? So the UV divergence as usual is cut off by this, right? And the IR divergence is cut off by capital R, right? Because when you look at the integrals, right, you have to do this integral d for y, right? And the only part of y that is relevant is which is below capital R, right? So that's where the IR cutoff comes in. Right? So this part of the, so in the QFT language, right, this part of the log is the IR log, right, and this part of the log is the UV log. In epsilon, we'll see what epsilon means, right? This will this epsilon controls whether it's the late time behavior or the early time behavior, right? Because when you take a Fourier transform, right, log of omega plus I epsilon has one kind of Fourier transform, and log of omega minus I epsilon we have a different kind of Fourier transform, right? So and that's what controls late versus early time.
In the first log, yeah, in the IR log, you're saying the I epsilon doesn't depend on incoming outgoing.
Exactly. Yeah. Yeah. See, this IR log, I mean, the physical way to understand this, right, is that this scattering produces some gravitational wave, or the gravitational wave form, and that has to propagate in the background of all the particles that is there. Right? That propagation is, the effect of that propagation is this one. Right? So this is always in the future. So this will control the behavior in the future. Okay. So then we just add the two, right? T hat x and T hat h, right? Because you have explicit expression for T hat h and you have explicit expression for T hat x. T hat x was this delta T hat x. And now you have to Fourier transform, because ultimately you are interested in the position space waveform. Right? So the position space waveform is basically the Fourier transform of this combination, because this 2g over r times T hat x plus T hat h is E tilde, right? And we are now Fourier transforming that E tilde to get our E. Okay. And if you recall the kind of expressions that T hat x and T hat h had this log of omega with some I epsilon prescription, log of omega plus I epsilon or log of omega minus I epsilon if eta is negative. And now we are going to use these Fourier transform rules. This again is something that you can easily verify, right? That if you have an integral of this kind, okay, where this is where the integrand has this logarithmic singularity near omega equal to 0, okay, this translates in the Fourier transform language as a behavior where it goes as minus 1 over u for large positive u, and it goes to 0 for large negative u. The fact that it goes to 0 for large negative u you can perhaps see easily, because if u is negative, then you can close this contour in the upper half plane, right? Because then in the upper half omega plane, this is convergent, and the pole or any singularity, the branch cut is lying in the lower half plane, right? So once you close the contour in the upper half plane, you can just shrink the contour to 0 and you don't get any contribution. Okay? That's why this vanishes for u goes to minus infinity, but it has this feature for u goes to infinity. And this has the opposite feature. Okay? So using this, we can now translate whatever we calculated here, okay, into the position space language. Okay? And that's precisely what gives us the expressions for the B and C that I showed you. Right? B is the coefficient of the 1 over u term at late time, and C was the coefficient of the 1 over u term in the early time. Is this clear? Are there questions?
You wanted to calculate the full signal, not just the memory part. You would have to do the full Fourier transform of the omega inside those. I mean, instead of just the asymptotic value.
Yes. Yeah.
Supposing I want the full epsilon.
Yeah, if you want to calculate the full signal, then there are many other things that you have ignored, right? Because you are doing a low k expansion, right? This iterative procedure itself.
Soft is probably okay for the full signal also. That the energy of the graviton is less than that.
Yeah, true, but okay, then for example, you have to this e to the I k dot RA, right? You cannot simply say this provides a cutoff. You have to also keep the dependence on this RA, RB.
Yeah, the asymptotic is a soft thing, it's not a full.
Exactly, yeah, yeah. Right? So the full finite time signal you will not get, right? But you can ask that this is, say, we are getting 1 over u, then log u over u square, right? Then higher order. But in that, instead of getting log u over u square, you can ask what about 1 over u square, right? It's still late time, okay? But 1 over u square, and that will be controlled by what you are suggesting, the corrections to this, okay? But there you have to be also careful about to keep all the RA RB dependence and so on. Okay? In principle, it is possible to do if you want to do that. But this whole analysis is only for the tails, right? Things which go polynomial in 1 over u, right? If there are quasi-normal modes, for example, where the signal decays e to the minus k times u, okay, that you will not get from this analysis, right? It's only the polynomial decay at late time, which translates to singular expression in the omega plane, in the omega space. Those are the ones you can, in principle, capture by this method. Any other question? Okay. So now it's clear what to do in the next iteration, right? We just have to take the solution that we have found here, right? The t hat that we found here. Now calculate the E, okay? And then use that to calculate correct the trajectory, and use that to calculate the new contribution to the gravitational energy momentum tensor. Okay? And effectively, what happens is this gives rise to integrals of the kind that you saw, but those are like two loop integrals, right? You have integral over not just one d4l, but d4l1, d4l2. So certainly I didn't have the courage to do this, but Vishwajit managed to do those integrals as well. Okay? And in that process, he reproduced exactly what I quoted as the coefficient of log u over u square terms. So this is the current state of affairs, right? That we can do explicit analysis up to this log u over u square terms. But in principle, there is no reason why you cannot extend it to higher order. Okay, even though the soft theorem by itself doesn't tell you anything about what those higher order terms will be. Soft theorem stops here. Okay, so now let me just make a few comments and then I'll end. So what I think I have convinced you that the classical analysis is straightforward, right? It may be complicated, but there's no subtlety there, right? We are just solving the equations iteratively. And in particular, it does not involve the complications of infrared divergence and phase ambiguity, etc., that the quantum soft theorems suffered from, right? As I said, in 4 dimensions, the quantum soft theorems have those issues and you have to deal with them. So from that perspective, one may feel that the classical analysis is certainly better than trying to go via the soft theorem. The point we should keep in mind, however, is that it's the quantum theory that teaches us the right question for which you have the simple answer. Right? If you are trying to solve this as a classical problem from the beginning, right, we wouldn't specify initial and final state of matter and ask for radiation. Right? As I said, the typical classical problem will tell you, I'm giving you the initial configuration, right, of matter, no radiation, you evolve them, you find the final configuration of matter, and you calculate the radiation that came out of it. That's a much more complicated problem, right? And that is not something that you can solve very easily. Okay. What quantum theory taught us via the soft theorem is that if we change the question, if we say that I know the initial configuration of matter and final configuration of matter, and now you ask what kind of radiation comes out of that process, okay, that question has an easier answer, has an easier solution, okay, and that's what we should address. Right? And once you know what questions to ask, then the classical analysis becomes straightforward. Okay, so this is what I have said here, okay, that quantum theory is the one that teaches us to specify both the initial and the final state of matter and then ask for radiation emitted during this process. So that, I think, is in some sense the central role of what quantum soft theorem taught us. Right? Even though now we don't need quantum soft theorem, we can just do a direct classical analysis to get all the results. And finally, let me just say possible generalization. And this I have already discussed earlier, that there is reason to believe that the coefficient of u to the minus n minus 1 log u to the n, these terms may also have universal properties, in the sense that they also depend only on the initial and final moment of matter. Okay. Matter here means hard gravitons also, right? If there is a hard gravitational wave emitted, it also could depend on those. So if this is true, then the next question is, can you compute them? Right? It's just not enough to know that they are universal. You also know we need to know what expressions they have. As I said, soft theorem is not useful anymore, but direct classical analysis may be possible, and this is still some work in progress. Okay, hopefully it will see the day of light at some time. If we can do this, right, then what it is telling us that we have, by looking at the coefficients of these terms, give you infinite amount of information about the momenta of the incoming and outgoing particles, right? Because one coefficient gives you one combination of momenta of incoming and outgoing particles, right? The more coefficients you have, the more information you have about the momenta of ingoing and outgoing particles. Okay? So if you have really infinite amount of data, okay, then it's perhaps not too ambitious to hope that in terms of this infinite amount of data, right, we can reconstruct the initial and final state of the event that led to the production of the gravitational wave. Right? Imagine that someday in the detector we discovered these late time profiles, late and early time profiles. Right? Then we analyze them. We analyze them to extract the coefficients of these terms in the waveform. Okay? And then you use this formula in terms of which expresses those coefficients in terms of the momenta of the ingoing and outgoing particles, okay, and invert them to see if we can extract the momenta of the ingoing and outgoing particles in terms of those coefficients. Okay. So that's of course a much longer term goal, but hopefully we'll see some progress over time. So I think I'll stop here. Thank you.
May I ask something? So, when we usually think about solving classical equations of motion, we don't think of doing this, of setting some arbitrary final state, because in some sense, if you specify an initial state, you can only get one possible final state, right? So
True.
So is it consistent to think about it this way?
Yeah, I think this is the question that was asked. Here the point, you are not specifying what interactions you have. You take a given initial state, right? And if I am free to choose what kind of interactions I have, right, I can adjust those interactions to produce the final state that you are taking. Right? This is so. There is no inconsistency in giving for a given initial state, right, what kind of final state you may have.
Right? In some sense, you are just solving Einstein's equations, right?
No. Einstein's equations coupled to any other force, because inside the scattering region, anything can happen, right? So I can set up a bomb, right, inside the scattering region, which explodes precisely in a way that disperses the particles in the final state that have chosen.
Sure, but even those will be constrained by what you are allowed to do
by conservation laws, right? We are assuming that you have momentum conservation, but otherwise there is really no other constraint.
Okay, but in some sense, the local energy momentum conservation has to be. Right?
But that is not visible in the initial and final state. It is true that in the scattering region and everywhere else, local energy momentum conservation will have to be respected, right? But that doesn't constrain the initial and the final states, right? Because you can adjust your interaction so that you can conserve local energy momentum tensor, and nevertheless you deflect the final state a little bit.
Yeah, I had a question regarding the coefficient pertaining the memory effect. So
yes,
if you can go back to that expression.
Yeah, this one.
Yeah. So in doing this classical calculation, are we taking in consideration of the energy scales in any form, that this formula would be valid up to certain energy scales and after that it will break down?
No, as long as it's late time, energy here is translated into U.
Okay.
As long as you go to very, very late time, this formula is exact.
So in that case, my question was, then classically this R is the region of the scattering, right?
No, no, R is the distance of the detector.
Distance
Right?
of the
We place the detector at null infinity, right? So R is that distance.
Okay.
The scattering region is this L, okay, which that didn't enter here. It entered in this in the argument of the log. That's the scattering region.
Oh, I see, I see.
Right? So this memory term doesn't care about the scattering region.
Okay. Yeah. Thanks.
I had a
Yes.
question. So there are people have been thinking about hyperbolic, just scatterings of black holes,
Yes.
hyperbolic orbits.
Yeah.
So there you actually know the initial and final momenta. No?
Yes.
So would this be useful for that problem?
Yeah. See, people have. This is valid for any scattering, right? In particular, this hyperbolic trajectory is where you only use gravity to do this scattering. Right? That should also obey this relation, right? In fact, not just this memory relation, but all the other relations that we have, and people have checked that. So they have the answer. They have the answer not just in the late and early time, but they have the answer for all times, or in frequency space, they have the answer for all frequency domain. But if you go to low frequency, right, this provides a test that if you don't reproduce this, right, then there's something wrong with the calculation, because this is has to be valid in general. Yeah, exactly.
In the low frequency full trajectory calculation, and the low frequency gives you this log term.
Yeah. Yeah. So, people are also doing these kind of calculations for eventually applying to binary merger, right, by some kind of analytic continuation, because they do the hyperbolic trajectory and then they convert that into bound state problem. But this hyperbolic trajectory calculation itself, right, better obey these soft theorems.
More questions?
You said you had some remarks about the quantum effect. Classical.
Quantum, no, this is purely classical, right? Quantum effects mean the details of how you use the quantum soft theorem to get to the classical limit.
No,
right?
okay, so yesterday you showed this, that the number of gravitons, which is
Yes.
coefficient times h cross omega, is independent of h cross.
Exactly, yeah.
So you have a large number, which is the soft
Factor, yes.
So can you think of something where you have an order h cross omega effect, which can be observable using the fact that you have a large number of gravitons?
Yeah, the point is we have large number of gravitons, but so low frequency that I think it will be at least.
So high frequency may be possible.
High frequency gravitons, yeah, if you can produce high frequency gravitons, you may be able to see it. But again, I don't think that this kind of analysis will give any better handle on observing gravitons, right? You are thinking of observing individual gravitons, right?
No, any h cross order h cross effect.
Any h cross order h cross effect in gravity, but this has to be quantum gravity, right? It's not a classical effect in that case. Yeah, so what you are asking is that you have this distribution, right? Classical limit corresponds to the sharp distribution, right? The first correction will see the width. The number of gravitons is not quite fixed, but there is a spread. Right? That will be the quantum effect. Right? But to see that will be probably very difficult, because it's really very sharply peaked, right? Because the number of gravitons, it is basically the fluctuation is root n, right? Down by 1 over root n, and n is huge.
So you have to go to few gravitons to see the
Exactly, yeah.
And the problem of detecting.
Yeah, exactly. Then the question is how to detect those free gravitons, right?
Okay, so if no more questions, let's thank Ashok again.
Thank you.